Okay, next type of reaction is called double displacement. Unlike single displacement, where I had something that was all by itself, here I have two compounds, right, that are reacting. So if I see two different compounds, AX, BY, then I know this has to be a double displacement, right? Unless AX plus BY happen to give me one product, then that would be a synthesis reaction, right? But as long as I have two compounds and I have products, I have more than one product, it's definitely going to be a double displacement. Now, how this works and how I usually visualize it is similar to what you would do in your math class when you're multiplying two terms, right? I do kind of a outside, inside look, right? A goes with Y, X goes with B, but be careful. A and B always are first, right? Some people end up writing XB over here, but that's not right. That's not what you're supposed to have. You're supposed to have BX. The metal always comes first. So make sure you write it correctly, right? But you're just flip-flopping the partner that that element has from one side of the equation to the other. So these reactions are fairly simple. It's pretty easy to follow along with, or it should be, right? Our first type of example has precipitates involved, right? So we're going to have a formation of a precipitate here. I showed you a reaction in a demo that looked like this. I had two clear aqueous solutions. One was sodium carbonate, the other one was magnesium sulfate. Excuse me, I can't write a Q for some reason. And I put those two things together in the same beaker, and things changed, conditions changed. Because now instead of the sodium staying with the carbonate, that sodium could go with that sulfate instead, and the magnesium could go with the carbonate. So I'm going to write two new products here. And I'm going to go down below because I'm running out of space. But I'm going to make, again, it doesn't matter what order you write it in necessarily, but I'm going to make a sodium sulfate. And I'm going to make a magnesium carbonate. Again, be careful to make sure those formulas are correct. These are correct currently, right? Because sodium has the +1 charge. Everything else has a +2 or -2. So there should be one sulfate, two sodiums. There should be one of each, magnesium and carbonate. And the whole thing is balanced, too, because of that, right? There were two sodiums with the carbonate on the left, so two sodiums with sulfate on the right, no problem. But we knew that a reaction occurred in this case because we saw a precipitate, right? Our precipitate in this case was that magnesium carbonate, right? I know that because sodium is always soluble, and so is sulfate. So that was definitely going to be an aqueous part of our solution still. Those two ions, sodium and sulfate, were still dissolved in the water. They didn't come out, but we saw that magnesium carbonate come out. It was that white crystal that came out and was at the bottom of the solution when you saw that demo. So it should be pretty obvious, pretty easy to tell that a reaction like this occurs because a precipitate formed when there was none previously. Two clear solutions, all of a sudden you have a precipitate that you can see. Definitely a reaction that occurred. Another example, and I might post a video for this one because it's kind of cool, right? I'm not going to do this one myself because you have to clean it up, and I don't feel like cleaning it up. But luckily someone will probably have done it for me at some point or another. So I have potassium iodide. And let's say we react it with lead nitrate. Again, plumbous nitrate, lead-2 nitrate. You got to make sure you're paying attention to the charges on things. But this reaction is going to look a little bit different. I mean, everything's the same technically. It's just going to look different because I'm not going to get a white precipitate. I'm going to get a different color altogether. So again, I just kind of flip-flop things, right? I'm going to put the potassium with the nitrate now, right? Outsides go together. So I make a potassium nitrate. Both of those have 1 charges, so it should just be a 1-to-1. I'm going to put the iodine with the lead. And again, you have to write your lead first. Pb lead iodide. It is going to be a little 2 here with that iodide because lead has that +2 charge still. But in this case, I'm also going to make a precipitate, and that precipitate is going to be that lead iodide. That's supposed to be a down arrow behind it, but that didn't look very good. Try that again. There's my precipitate. There's a reason lead used to be in paints, right? We used to put lead in paint because it salts. That precipitate on the right, that lead iodide, is a bright yellow color that's really actually kind of hard to make in nature, right? Not that there aren't yellow pigments, but those pigments degrade very easily, whereas this one would not, right? So that paint would stay bright yellow over time, right? So we use lead for that purpose. We don't do it anymore because children tend to eat lead paint because it tastes sweet, right? It's another property of lead as an ion. It is sweet. It tastes good to that child. They know nothing other than put things in my mouth, explore my world around me, and they eat the paint because it tastes like it's sugar, right? So their primitive brain is thinking, ooh, this is food. And that's just the way it works. So it's not that they know that it's good or bad, they just taste sweet, so they eat it. Whereas the potassium nitrate is still going to be aqueous, it's still going to be dissolved in that solution. So those are just a couple different examples. Again, I might post a video for that because it's pretty cool looking. Formation of a gas, right? This one I'm also not going to do for a couple different reasons. If I had an iron sulfide, right, solid, and I reacted that with hydrochloric acid, again, probably aqueous in solution. I'm going to make 2 products here, right? Again, I just kind of do outsides, insides, so I'm going to do an iron chloride over here. Again, it doesn't matter which kind of iron that is, and that was an iron 2 sulfide, because sulfide has a -2 charge. That iron must also have a 2 charge, a +2 charge. So it's ferrous chloride as a product. But then I'm also going to make this, put hydrogen and sulfur together. Again, hydrogen would have a +1 charge. Sulfide has a -2. So when I put these together, excuse me, it's going to look like this. But again, I'm going to have these 2 products. I'm going to know that this reaction occurred because one of these 2 products is still soluble, but the other product is not ionic, not actually, right? That dihydrogen sulfide is a molecule now, and it's going to be a gas at room temperature, so I should see that bubbling out of solution. Now again, I'm not actually going to do this reaction as a demo or otherwise because that stuff really stinks, right? Dihydrogen sulfide smells like rotten eggs, and it's also poisonous, and it's corrosive, and it's extremely flammable. A lot of negatives to go with that, so I'm not doing that in class for a demo or for you guys if you were here. But when you see this reaction, when you see a gas forming, it could still be a double displacement. This is a double displacement. It's fairly unique because you made a molecule now, as opposed to 2 ionic compounds. Hydrogen with the chlorine was also technically a molecule, but it's very similar to an ionic compound because it's an acid. So flip-flopping partners again, same idea, right? Just make sure you balance charges. Think of it as an ionic compound because I know that there's going to be 2 here, 2 hydrogens, because the hydrogen would normally have a +1 charge. Sulfide has a -2 charge, right? Otherwise, I could also just put together the pieces. I should know that to make a molecule, I might need 2 hydrogens to satisfy that octet rule for that sulfur. So that's just another way to look at it, another way to think about it, but it's the same idea. I can also form water as a stable byproduct. So this is going to typically be an acid-base type reaction. So I'm going to have a hydrochloric acid reacting with, say, sodium hydroxide. Hydrochloric acid is an acid. Sodium hydroxide actually is a base. You may or may not know that. But it doesn't matter. You just have to put the pieces together, right? When I react these 2 things, I'm going to make 2 products. Again, different color there actually. The hydrogen needs to go with the hydroxide. But I also have to think a little bit there, right? +1, -1, it's balanced. But I have 2 hydrogens and an oxygen. That's not an ionic compound. That's a molecule again. I'm actually going to write H2O. That's water, right? So hydrogen plus a hydroxide gives you a water, right? That's, again, why this is formation of a water. But otherwise, the other 2 things still need to go together. I need to put a chlorine and a sodium together. Again, the sodium has to come first because it's the metal. So I'm going to write a sodium chloride as my other byproduct. Again, I just made 2 products, one of which is a liquid at room temperature, that water. The other one is aqueous. But those 2 reactants to begin with were aqueous. And they were both clear solutions. So this is kind of a hard reaction to know that occurs. But what I'm going to be able to do to see that this reaction occurred is use an indicator. Because I have at least one indicator in my possession in the lab that in acidic conditions is yellow, right? The color of this indicator is yellow, whereas in basic solutions, it's blue. So I could put that indicator into both that hydrochloric acid and that sodium hydroxide solution, and I'd see different colors. But then when I combine those 2 things together, right, if I get to a neutralization, if there's exactly a 1-to-1 ratio of hydrochloric acid and sodium hydroxide, because this equation is already balanced if you didn't notice, right, then over on this side, that solution is actually likely to be a green color, right, because there's a transition from yellow to blue, and when you have yellow mixed with blue, it makes it green, right? So I am going to know that this reaction occurred because I could use an indicator to see that it occurred, right? So your indicator, right, all that does is help you determine what pH you have, right? Because as that pH changes, that's going to cause a change in color for your indicator. So you can tell that a reaction occurred because a separate reaction is happening with your indicator,